Hi everyone, I hope everybody is doing great. I have been receiving a lot of requests after my first lecture on how to use crystal plasticity theory to model FCC crystals. A question I received later was how can one use user material subroutine in the crystal plasticity framework to model HCP or hexagonal close packed crystals such as alpha titanium. So I'm not going to go into the details of theory, but today I will keep it more practical. So if you want to learn about the theory of crystal plasticity, then please go back to my lecture, whose link I have provided on the top, and then come back to this lecture for practical purposes. What I'm going to present today is I'm going to present how to model HCP crystals and how you can identify the parameters involved using uniaxial test data. If you look at our frameworks, we have crystal plasticity framework, which accounts for elastic deformation, which also accounts for plasticity due to slip-based deformation. Also, it can account for defects, micro defects, and damage in the material. And also, it takes into account the crystal orientation effects. This is what we're going to cover in this lecture. I'm going to show you one of the crystal plasticity user material subroutine, which has been adopted from Professor Marine's group. And this was the initial version, which we slightly modified and tailored it for HCP crystals. We then later extended it for dual phase materials and also for transformation induced plasticity, as well as for the case if you have material degradation due to environment assisted cracking. So those models are more complicated. I will show you today to how to model HCP material using this first a very primitive UMAT user material subroutine, which accounts for HCP crystal plasticity theory. So let's jump into it. So here you see on the screen the code, and as you can see, there are quite a lot of files as compared to the previous user material subroutine, which was from Professor Huang. This material subroutine has a range of files which you need to really deal with, and I will explain one by one each one of them. I will also upload the PDFs associated with this model, and those will be available on my website www.professor3meg.com. By this time, if you haven't liked my video and not subscribed to my channel, then please subscribe to my channel and also like the video so that the algorithm can send this video or push this video forward to more users so that they can benefit from it. So please do that. Now, so what you have here is you have an HCP.sx file. This file is the one which defines all the material parameters which are involved in an HCP crystal, or to define the properties of the HCP crystal. I will come back to this or each one of these later. Then you have some parameter files. In the current case, we don't need that, but there are some parameters which you can define in this parameter.inc file. And also there are some crystal parameters which you can define in this param_crystal.inc file. At this point, I would like to request, please like this video and also subscribe to my channel, as our subscriber numbers are very low. And also, if you don't like it, then the YouTube algorithm will not push it to the other users who may benefit from it. Please do me a favor by doing so. Thank you very much. And here you have to change the codes again. For the current case, we're going to keep everything default. But later on in the advanced level, when we go in some other video, I will show you how you can change these parameters and change the way the subroutine really works. We don't need this py file. This was just for myself to get the results post-process automatically. Then we have an input file. In this case, we have one element model with uniaxial loading, which you already are familiar with. I have many videos on how to create a uniaxial model based on that. The only difference here is you have to define a material card with the dependent variable of this, and these variables are dependent on the number of state variables which are involved. Again, the documentation gives you all of these numbers as well. And then user material constants are 2, and it says 1 and 1. This means it will take all the data from the user material subroutine and this hcp.sx files. Then you have a test file which is test.xtali, and this is another input file. Whenever you have an I at the end, this means it's an input file and you need to really pay attention to that. And this defines the overall simulation parameters, which can also be taken towards the ABAQUS simulation as well. And again, I will explain that in next few minutes. And then finally, we have a texture file here. And in this texture file, you define the number of grains, which is 300 in this case, and their orientation. As you see here, these are the Euler angles. And in this case, we are using 300 grains, but I think in the file, we have around 500 data of up to 500 grains. So when you do simulation, it can do homogenization and it can treat it as a polycrystalline material. And initially with one element model, you can specify how many grains this one element has. And based on the experimental data, you can fine tune the model parameters to fit the stress strain data at macro scale. So in a way, this model is different than the Huang's model. In that case, you were dealing with one grain at a time, but in this case, you do homogenization and each element can have as many grains as you have the texture orientation in this texture.txti file. Okay. And then this is the main subroutine. And again, you can see the subroutine is for crystal plasticity and it has all these things defined. Again, you can have a look at that. The only thing you will have to change always is you have to change the directory where all these files are. And I will come back to that, how to change it as well, depending on all the file where all these files are stored. So for Unix system, you have to use forward slashes as shown here. I have commented it down because I am on the Windows system, and for Windows system, you have to use backslashes rather than the forward slashes. So you have to be careful about all these things. Okay, so now first things first, we all understand this is a texture file. We don't need to do that. If you have your own texture data from your EBSD analysis, you can put those Euler angles here directly, and you can create your own texture file as using the as many number of grains as possible. Then test.txti, this tells that in this case we only have HCP. The code is only for HCP, but it can be used for BCC and FCC as well. So you have to give the ID of the crystal ID or crystal type. In this case, we are using HCP. If you do 1, then it will call the subroutine for FCC and similarly 2 for BCC. And then we define the number of grains. And as you can see in the texture file, I said 300. So we're going to use 300 grains here. I can use 500 here as well because there are 500 number of grains. Then it says that all the single crystal input data, which is material parameters, are in this hcp.sx file, which you remember was this file. I will come back to that in a few minutes. Then ODF code 1. So this is for the case that you want to use the texture file to. So this defines that the code will use the texture file, which is this texture.txti, to get the orientations. Then multiple number of increments to output texture. Again, how many output you need. Again, if you increase the number, your file will get bigger and bigger. So in this case, we are only asking for multiples of 10. You can make it 100. You can make it 1 as well to get more output as well. And all the texture output will be written in texture.txtio. So this is the current or initial in texture. But in txt, texture.txto will have the output texture and it will write after every 10 multiples of increments. So how the texture is evolving, it will write that, and then you can really plot that as well using any mtext type software to see how the orientations are changing with the deformation, to see the effect of deformation on the texture itself. And these are the toleration, iteration state, and these are the variables. You can just leave it for the time being. It's just about the iterations. It has to use maximum number of iteration. For global neutron iteration as 20. You can increase it if you think you are not reaching to convergence in your case. But these are default values. I never change them. They are pretty stable. It also goes for line search algorithm if you have loss in stiffness. So line search algorithm helps you, and it provides these parameters for ABAQUS as well. And then some other information about the cases. So these are all default. You can read through it and you can find out what is what here. So normally we only play around with these parameters max, and that really is enough for us. Otherwise, these other convergence criteria are very much the same. Here, I think I already explained to you what these things are. Now, if you go to the material parameter file, then you have two IDs. One is your elastic properties of the crystal can be defined as isotropic or anisotropic. So since crystalline structure is always anisotropic, so we're going to define it as 2. And for the case of HCP, we need to define these 5 variables. If you remember, for cubic crystal, we need 4 coefficients. Also, you can define thermal expansion coefficient in different direction if you're doing some thermomechanical analysis. You also have to define the C over A ratio. I have taken this value again from literature. For the case of HCP, again, you can look into the theory and see how you can compute this for a specific crystal. Now comes the part that how many families of slip systems will be activated in your crystal. And in this case, the total number of possible ways which can activate in a HCP crystal are 5. So there are five families which are defined here. 5 families which are defined here: basal system, and these are the slip system here, which is 3 different types as I see. Then we have prismatic system, which are these ones. Then we have pyramidal system, which have all these 6 systems. And then we have pyramidal C plus A system, which are 12 different variants. Then pyramidal C plus A, which is second order systems, and there are around 6 variants. Then we also have tensile twinning and compressive twinning systems as well. So again, I'm not going into the theory of that. You can have a look and see which systems are activated in your case. What you have to do is you have to find parameters for each one of those system families. And to do that, obviously, if you are working at a single crystalline level, you need to do the uniaxial testing for those orientation which will activate these families of slip systems separately. And then you identify the parameters for each system. If this is not the possibility to get the single crystals, because normally HCP is very challenging to get the single crystals. They are generally in the form of lathes and plates in microstructure, so it's not easy to get that kind of structure. Then in that case, you can also try in polycrystal material a nano indentation test, and for each test you can identify these parameters from that. Again, I have a lot of videos on nano indentation test as well and how to identify parameters from that. In that way you will do it. In this case, I keep my life simple. I'm using the same set of parameters for same hardening, initial hardening for each one of them, while the initial yielding, initial resolved shear stress and saturation resolved shear stress, I'm using it based on the ratios which are again prescribed in different papers where they have investigated the deformation behavior of alpha titanium alloy. So everything is motivated from that. So coming back to where we were, there are 5 modes which are possible as per the file. And in this case, we found out that these 3 modes are more significant, or they are the ones which were activated for this specific crystal or this material, alpha titanium material. So which are 1, 2, and 5. 4 and 3 are irrespective now, because we say that the maximum number of modes out of 5 will be first 3. So 1, 2, and 5 we have mentioned here. They will be the first system which will be part of the simulation. Rest of them will be ignored. If you say 5 here, then it will be in this order, as you see. Number of vertices for each single crystal system is 121. Again, you can look at the theory, and the data is given in these files. We never change this file. They are always fixed. So you can see for the titanium also, we have these files here, and they have all this data as mentioned here. Now for basal system, we have mode, which we call it mode ID number 1, which is here. Then we have number of variants or number of slip systems, and then how many are there. So, and then we have rate sensitivity exponent and the strain rate, initial strain rate behavior. If you remember in the crystal plasticity theory, we have gamma naught dot and also an exponent, and these are basically these two variables. Then we have a B drag. Again, you can look at the theory where they define the hardening law. So these are all hardening parameters here. So this is the initial hardening, this is the initial yield, saturation, yield, hardening, kappa naught. So again, the hardening model here is very rigid in my opinion, not many parameters, but so most of the time you play with these parameters and this parameter, and rest of them remains the same. Similarly, if it's a rate dependent case, then obviously you have to vary these parameters as well. For the time being, these are very low, and this means we have set it to rate independent case. So again, if you look at the theory first PDF file, I will upload with the same thing, then you will understand more about these parameters. The hardening law is slightly different than what you found in Bassani and Wu model and also Penn model. Similarly, for the second case also, we have the same set of parameters as you third also. So all of them have same hardening models, but parameters can be different, and you can see they are different in different cases. So this is how you define the parameters. You have to start with some initial guess, and then you have to run the simulation. So to run the simulation, command prompt, and I will go. So here we are in the folder. Remember, we have to change the path in the user material subroutine file. So here the path should be the same as where everything is. So I'm going to I have copied the path, and this is the path I have. So I have change it to this one. So now everything is set up. In my opinion, what we're going to do now, we'll just run it. ABAQUS job equals to SXTAL, because this is the input file. User equals to UMAT. This double precision, and interactively run it. Now when you run the job, it will first compile, pre-process the data, and then run the simulation. So as you see now, everything is finished without any problems. So now I will go and open ABAQUS. I will now go to the folder, and I will look for the ODB. And this is the file, you remember, as STAL. And this is the one element model, and it looks something like this after deformation. Now what I can do, tools, manager, create, field output, stresses in S11. So we go with LE log, strain in one direction and stress is in one direction. Select the element, save absolute values, and then create, operate on XY data, combine trains, then stress on vertical axis, save, and then plot. So you see, this is how it looks like. Generally, alpha titanium in this was basically from TI 5553. So this yields around this kind of stresses. So you can see it is going this way. Again, the units are, you need to get to the megapascals, you need to multiply it with 10 raised to power 6, and that will be in megapascal. The units are made in this way. In our case, you can change the units throughout as well. We work with micrometers or something in this case. So this is how it looks like. Now if you want to change, let's say you had a stress strain curve and it's slightly, let's say, higher than what you expect, then you go back to this, and then maybe start playing around with these parameters. So let's say you can make it 100, and maybe you can make it 150. I think this is the first mode. You can play around with the others as well. You need to change the ratio of the others as well. If you look at the paper, I forgot the reference, but there has to be a certain ratio among different families of these slip systems in terms of the initial resolved shear stress, which will activate the plastic slip in different families. So you have to really be consistent with those literature. So again, I'm going to run it again. Let's see here. At this point, I would like to request, please like this video and also subscribe to my channel, as our subscriber numbers are very low. And also, if you don't like it, then the YouTube algorithm will not push it to the other users who may benefit from it. Please do me a favor by doing so. Thank you very much. So now, as you can see, this is also completed. So first thing I will show you is, I will delete this. I will close the ODB, then open the new one, create field output, same variables, select this element, save as is, and then create operate on XY data, combine strain then stress, and save it as the second data. And I will delete this. Then I will plot those, and you can see by changing the parameters, you can really shift the stress strain data as you see here. So I hope this makes sense, and if you want to fit the parameters, then you can really play around with the parameters, and that can change. And you have to do a lot of iterations, runs to fit the parameters, because as you can see, there are a lot of parameters involved in this case. So I hope it made sense. Yes, one more thing before I go. I told you that it will write the texture data in texture.this file. So this is the texture.txto file. I was the input file, so it should now write the texture data. So you see, this was the initial texture as it says. And then as you go down, so let's say after 300 grains, maybe this is after 10th increment, and you can see now texture has started to evolve along with integration number. And obviously there is only one element and one integration point, but number of grains, you can really link it with those number of grains. So you can use MTeX software to really plot the texture as how it evolves with the deformation. So it has written down all the texture data for us, as you see, for all 300 grains. So you can get the texture data as well, and you can use MTeX for that. So I hope this made sense. You can also use the same tool or same software or same code to do simulation as you did it for the with the UMAT of Professor Huang, where you can model individual grains separately, and rather than having this homogenization theory. And if you want to learn about that, or if you have any other problem which you want to simulate with this code, then comment below and I will tell you how you can simulate that as well. So I hope you understood what it is. It's a lot of things to digest, which I tried to deliver in a short time. Have a look at this, download the whole zip file with PDFs and go through the theory first, then these parameters will start to make sense as well. But as you can see, they look very similar to what you saw in my previous talk. So good luck with everything, and if you have any more questions, then happy to help. All the best.